All right, let's see how we would go about using these tables to find what tolerances to put on our dimensions. Let's start with a part that has a shaft that fits into a hole, and our design calls for a nominal size of 2 inches, a 2-inch shaft and a 2-inch hole. Nominal means name, and so a 2-inch shaft and a 2-inch hole will be our starting point, and then we're going to add or subtract tolerances to those. So let's see what we've got. Here is the first table for the running clearance fits. And what are we doing? We're doing a RC1. So when you're reading a table like this, you are not reading a novel. You are looking at numbers, and you need to make yourself slow way down and just look at everything, including the headings and the footers and the labels and so forth. So first of all, let's find where we are. We are looking for class RC1, so that's going to be this whole blob here. Means we can ignore all the stuff on the rest of the chart. And then we are looking for a shaft and hole with a nominal size of 2 inches. And over here it says nominal size range in inches. Well, there's no 2-inch thing in here. But this says size range, and so let's look for the one that contains 2 inches in that range. And here it is, between 1.97 and 3.15. Our 2-inch stuff will lie in there. May I recommend that you get, if you print this out on paper, or even if you're on your screen, get a piece of paper and cover up the stuff you don't want. And some people like to actually get a piece of white cardboard and cut an L shape in it. I'll show you what that would look like. So I'm going to put an L-shaped piece of paper over this table here. There, see, I blocked out all that stuff we didn't want to see, and we're only left with the part that we're trying to look up. So there's our size range right there, and here's our class RC1. Now, as we're looking at our table, we want to make sure we understand everything in here. So let's look at all these headings up here. And whoop, there's some words in here at the top. Values shown below are in thousandths of an inch. So when it says your tolerance will be plus 0.5, that doesn't mean half an inch. That means half a thousandth of an inch. So that's important. All right, so let's look up our tolerances. First, the hole. And we're starting with a 2-inch hole. This says our tolerance will be plus 0.5, so plus half a thousandth, and minus nothing. So that means if we write this in limits form, we'll have diameter 2 1/2 thousandth down to 2. How about the shaft now? According to this, for the shaft, oh look, it's not a plus and minus, it's a minus and a minus. So for a shaft, we'll have 2 inches minus 0.4 and minus 0.7. So in limits form, our shaft dimension will be diameter. Look at that, those sizes are less than 2. So here are the sizes. May I recommend that you use a calculator when you're doing these? Don't try to do this in your head. That's a good way to go off the rails. I know if you're like me, I'm always feeling cocky and thinking, oh, I can do this in my head. And sometimes things go horribly wrong. So really, check yourself with a calculator. And when you do, these are the sizes you will get. Now, so we've got our hole size and our shaft size. They are these. I had to put my shaft size dimensions down below because I ran out of space. Let's check and see how much clearance we've got. So we'll look at the worst case, the maximum material condition, and remember that's where the part will weigh the most when it's on the scale. So the smallest hole and the biggest shaft. Maximum material condition for the hole will be what? Smallest hole, 2 inches. And maximum material condition for the shaft will be the biggest shaft. So 2 minus 1.9996, we'll get a clearance of 0.4 of a thousandth in the worst case. What about the best case or the loosest case? At least material condition, we'll have the biggest hole, 2.5 a thousandth, minus the smallest shaft, we'll get a clearance of 1.2 thousandths. So what? Well, this is handy for checking your work. Let's go back to our table here. So these are the dimensions we got, and here's where we did our subtraction and we figured out what our clearance would be at MMC and at LMC, worst case and loosest case. Now let's look at our chart. See this column that says clearance? There it says your clearance will be from 0.4 of a thousandth to 1.2 of a thousandth. Look here, that's what we got. So we just checked our work and we found out that checks out. We got the clearance we should expect to see. You could also find the very loosest tolerance for these 2-inch shaft and hole. So here's our table with the RC9 column. And here I am using my L-shaped piece of paper to block out stuff I'm not interested in. Notice that in the RC9 class, the hole is 7 thousandths bigger and the shaft is much smaller. So you can see here you're going to get a much looser fit than you got with the RC1 class. Well, let's go on and look at a force interference fit. Let's do a class FN1 for our 2-inch shaft and hole. So here is the column of numbers for class FN1. We're looking for the 2-inch range. So let's look in our nominal size range and notice that the numbers are arranged differently in the force interference fit. But we can still find our 2-inch nominal size. There it is in there, from 1.97 to 2.56. And here's our FN1. Okay, let's look up the hole. So according to this, for the hole, you will go from plus 0.7 of a thousandth to minus nothing. So there's the dimension for the hole. Then for the shaft, now this is an interference fit. So for the shaft, these are all pluses. We're going to add 1.8 thousandths and add 1.3 thousandths. So the limits tolerances for our shaft are these. All right. So let's check this out. What have we got? Look here. We've got a shaft that is always bigger than the hole, no matter what our tolerance range is. Let's check and see by how much. So first, worst case, let's check the maximum material condition. So smallest hole, biggest shaft. Smallest hole is 2 inches. Biggest shaft is 2 and 1.8 thousandths. Well, 2 minus a bigger number is going to give us a negative number, which is good because this is supposed to be an interference. So worst case, we'll have an interference of 1.8 thousandths of an inch. Best case, least material condition. So least material, biggest hole, minus smallest shaft. Looks like we're still going to have an interference, but less interference, 0.6 of a thousandth. Let's check that out. So here's our table. Here's where we looked stuff up. Here are the two interference numbers we got. And notice here is a column in our table that gives the interference we should get. It says our interference should range from 0.6 of a thousandth to 1.8 thousandths. Look, that's what we got. So that checks out. Looks like we did our tolerances correctly. The numbers that we got match what ANSI says we should get. Now, here is the assignment that we're going to do. And in a separate video, we'll go look at how you might put these numbers into your CAD drawing. But here's the basic idea. We've got a caster with basically a bolt as the axle. It's a hex head threaded rod thingy. That's the axle, and that fits through a bushing. So here's a bushing up here. That fits through the bushing. And we want the axle to turn freely inside the bushing. So between the shaft and the hole in the bushing, we're going to have a running clearance fit. And this says it'll be an RC7 class of fit. Then we're going to press fit the bushing into the hub. So this bushing gets pressed into the hub. And because that's a press fit, we want an FN, we want an interference fit. And according to this, this will be an FN1 class of interference fit. And this will be a nominal diameter of 1 inch, a 1 inch outside diameter on the bushing, and a 1 inch inside diameter on the hub. But now we'll go to our chart and look up what tolerances should we add or subtract to those two dimensions to get the class of press fit that we want. So now we'll go look at AutoCAD and see how we can apply these limits dimensions to our shaft, bushing, and hub.